All right, everybody, welcome to ACCU 2021 virtually. My name is John Lakos, and I was planning to give this talk a year ago. Unfortunately, the universe had other plans. Today, working with me is Vittorio Romeo, and he is the co-author of yet another book that's coming out soon. And he gave a presentation on that this morning. Vittorio, you're there, right?
Yep, I'm here. Hello, everybody.
All right, awesome. And so this talk is about a book that came out at the end of 2019, beginning of 2020. It's something that I've been working on forever. It's the first of 3 volumes, and we'll get into that in a second. And it's available. And what I'm going to do today is give you a little introduction to that. And we're going to have 2 points during the talk where we can ask questions, and then there'll be questions at the end. So when the time comes for questions, please be sure to write them in or however that works. And then Vittorio will ask me, since I've set up with only one screen. And with that, let's get started. So this is me. This is my book. This is me with my book. And we're going to talk about chapter 0 today. It's a big chapter. It's got a lot of interesting information. It's the motivation, and the rest of the 3-volume set is an imp detail on what we're trying to do. The motivation is hierarchical reuse, and it's a way of doing business that is faster, better, cheaper, all at the same time. And it's not something that comes for free or immediately and requires a great deal of investment. There are 3 more chapters in this volume. The volume is called Process and Architecture. There are 2 more in my head. They involve design and implementation and verification and testing. So with that, let's get started. So this may seem familiar. This is that faster, better, cheaper triangle from Rapid Development. And it's an important concept in software engineering that if you are trying to design something and you want to do it quickly and you want to do it on a given budget, then the product is going to suffer, meaning the quality. If you want to do something that's as good as it can be and on a fixed schedule, then cost is going to go out the window. That kind of describes the budget for the book that Vittorio and I are writing. When you pick 2 of them, the third one's kind of determined. So over time, if you look at the sort of the faster, better, cheaper options, what we'd like to do is we'd like to expand the space over time. And that's what we're going to talk about today is how do you, through some process, improve the union of the faster, the better, and the cheaper component, and also expand the options as to what can be done in terms of trading off faster, better, and cheaper over time. So how do we do this? So if you imagine design, pure top-down design doesn't work very well. The problem is that there's an exponential amount of repetition. What I mean by that is if everybody in the world had to reinvent a string class, that would just be very bad for many, many reasons. One of which is that there would be a string class for every program. We wouldn't want that, but it's much worse than that. So we need to do something that addresses the issue of reuse. So top-down or application software is typically top-down, collaborative, and malleable, whereas library software is typically bottom-up, reusable, and stable. And we're going to look into a little bit what that means shortly. Imagine you're writing a complex application. If anybody's ever tried to do this, you know that specifying it is difficult. The edges are very rough and they change with time. Even while you're trying to specify it, they can be changing as you go. The good news is that within the application, we know that there are regular pieces that will need to be built. So if you're in any particular domain, you know that you can build a particular subsystem, and that subsystem will be usable in this application as well as others. So the smallest subsystem might be a standard component. We might have many standard components. And in fact, the standards committee wisely decided to create a standard library. We have a standard library, and those pieces are used repeatedly, and they're the beginning of hierarchical reuse, but they're neither the top of hierarchical reuse or the bottom of hierarchical reuse. They're a lower middle point in hierarchical reuse. Now, if we go up a little bit from these components, which are themselves quite complex, we get larger pieces, and this might be a familiar subsystem in an application. Or we might have a subsystem built out of smaller pieces or many smaller pieces. And so what we get is this, again, hierarchical reuse, because the smaller pieces are being reused to create a larger piece, which is in turn reusable. So if we don't try to achieve this kind of reuse, we'll have a small library, let's say the standard template library or the standard C++ library, and then we'll have a lot of code repeated in applications as indicated on the left. If, however, we're very mindful of trying to allow for reuse, then what we'll see is we'll have a hierarchy of libraries, and we'll have small applications. And the small applications are far cheaper to maintain because they're smaller. There's less code there, there's less repetition. And I think it would be pretty clear that, you know, a small program that does the same thing as a large one, all things being equal, is a better thing. Now, obviously, there's a readability issue, but I don't think that they're competing in this particular case because the high-level applications are built out of large, well-thought-out pieces. Okay, this is a good idea. So imagine we start with a blank slate. We're thinking of building something. And if we don't think about it too carefully, we wind up building a big blob. And I'm calling this blob of software the cracked plate, because the boundaries in the middle of the system are really they're fairly arbitrary, and the complexity across a boundary is roughly the same as the complexity within a particular region. So this solution is brittle. It's also not well factored. My classical comical analogy is the toaster toothbrush, where you imagine that the mom says, "Come downstairs, brush your teeth, and make toast," and the child decides to build itself a toaster toothbrush. And it's one monolithic piece, and it's practical for the job at hand, but not much else. Then you can imagine something that's a little bit more well partitioned, and we'll call this collaborative. And you can see that here we have a circle that's partitioned in a fairly interesting way. Clearly, the pieces are aware of the other pieces, but they're not dependent upon them. And I would say that this is more like a toaster with a hook and a toothbrush with a hole. And they were designed to work together, but who in their right mind would go to the store and buy a toaster with this ugly hook sticking out of it? So this is probably not what we mean by a reusable component. So brittle software is usable within a single system, not a multiple versions of it, but a particular version, because when you go to the new version, that piece doesn't work necessarily anymore. If you have something that's more collaborative in nature, it might work through many versions of a system, but it's not necessarily going to work when we go across systems. So this would be the middle ground. And then finally, reusable software is designed to work across many versions of many applications. And the true value of reuse is therefore exposed. So now we might imagine we have a bunch of reusable things that are easy to describe. And they might have a particular color, and they might have a particular shape, and we can describe them as a dark triangle, or a dark gray square, a light gray rectangle, or a white semicircle. And you know, this kind of thing is easy to describe, and it gives the impression that the interface is easier and less complex than the implementation. So we say it has a small surface to volume ratio, even though that's sort of a metaphor to say that it's got a nice, easy to understand, easy to use interface, and it's got a high performance implementation, and that's a good thing. And we think of this in a factored world as having a toaster that makes sense, a toothbrush that makes sense, and an adapter class that makes sense. We compose them into a toaster toothbrush, just the same way as we would compose those other pieces into a circle. So back to our monolithic block of software. So if you have just one big, huge file of software, that's probably a bad idea. Now, historically, we had a couple of different design strategies. We had Dijkstra back in the day, who talked about hierarchical physical design, where each piece would be designed and put into place and then others stacked upon it. And it was his claim that if you did this and tested it with unit tests as you went, he didn't call them unit tests, of course, because it was a long time ago, back in 1968. But if you did do this, you would get a quality that's comparable to contemporary mathematical proofs. And mathematicians will argue about this. However, mathematicians are people, and people can have very elaborate theorems, and theorems can be wrong just because people are human. However, when you use unit test drivers, it has a different kind of testing that mechanically verifies things. So the combination of peer review and mechanical testing in a hierarchical way can produce very, very reliable software. So this is a good thing. And this is sort of the beginnings of large-scale physical software design. Then we have in a little bit later, 4 years later, we have Parnas talking about modular programming. And Parnas he was aware of and said that, yeah, that's a good idea. But what I really want to do is have really clean interfaces and encapsulate and hide the implementation so that when I make a local change, I don't have to affect other parts of my system. Now imagine we take the two of these, put them together, and add to it the notion of interface documentation, i.e. contracts, specifying exactly what is required in order to make this software work, and then what you can expect from it. And if those boundaries are carefully documented throughout the program, then you're going to have what I would consider to be a reasonable component-based architecture. So here we have something that's much bigger than components. We're talking about huge layers. Huge layers are unwieldy and not sufficiently fine-grained to be reasonably reusable. We could try to partition them further into these thinner layers, but if they're very wide, i.e. not granular, then they overlap other things. And again, it's hard to reuse something that looks like this in software. We could imagine siloed software. Now, this kind of software is great because everybody can work independently, but again, there is a lot of duplication at the lower levels. And so we want to avoid this kind of structure as well. So what is it that we want to achieve? And the answer is something that looks like this, where at the lowest level, we have stuff that nobody cares about: platform adapters, low-level interfaces, implementation utilities that would be even below what we would see in a standard library. Then at some point, we break out into what I'll call vocabulary types, which are the kind of types that you would use in the interface of functions widely throughout an enterprise. And an example of a vocabulary type would be an iterator or a string or a date. And of course, one of my favorites, an abstract interface, namely for an allocator. And in the standard, we don't have an abstract interface in C++11. We have a concrete type. Nonetheless, when we get to 17, we do have something that is a memory resource. And the idea of having the abstract interface be uniform throughout the entire enterprise, in fact, throughout the entire world, is critically important for interoperability. So the general idea is when you're trying to represent a value or a service that's ubiquitous, you want to have one C++ type to do that. Those are vocabulary types. Then there are utilities that work on vocabulary types, and those would be akin to algorithms in the standard library. And then we have sub-solutions, solutions, and then eventually we have high-level library software, which would be a complete subsystem in a large application. And so here we have, you can see that there are all these different levels, and anybody who wants to use this software can jump in at any given point in the hierarchy, because a level doesn't hide the lower level. The lower level is there and available and stable. So We look at finely graduated granular pieces. This is sort of like the physical side, and this is sort of the logical side. And if you look at the way this is broken down, we have a toaster toothbrush. It has a toaster, a toothbrush, and an adapter. And the toaster has a case and a chassis, and the toothbrush has a handle and bristles. The adapter has an arm and joints. And those are composed of subpieces and so on, till you get down to something that fits inside a single .h.cpp pair, which you can then implement and test bottom up. So if we look at the decomposition of this, suppose we wanted to create a toaster flashlight. We have a toaster toothbrush. We want to create a toaster flashlight. So classical reuse would say we would build ourselves a flashlight. So here's our flashlight, and then we would reuse it. The toaster depends on the flashlight. The flashlight is built however it's built, and we're done. But if we go look at finely graduated hierarchical reuse, we're not only going to take advantage of the scrub brush is going to take advantage of the pieces of the toothbrush. So you see how we put in a scrub brush, but we haven't designed it from scratch the way we did with the flashlight. Now the scrub brush is taking advantage of lower level bits itself. You see how the scrub brush is using the handle and bristles. Okay. So next, the way we would design something, if we were designing a function of many arguments, taking many arguments, we could design it this way with 6 parameters, and each of them would then depend on each of these individual pieces. That would be better, because if we do that, then it's possible we can extend it and reuse the bits individually. If we have only the one function, then we have to copy paste the function to function 2, and that's not so good. So hopefully we understand that whenever we're building something that's complex, like a function of 6 parameters, then we're not going to assume that it's not going to become 7 or 8 someday, and we're not going to want to copy paste that. It's a simple matter of proper factoring. Imagine we're trying to build something like a proxy inside a firewall connecting a client and a server. Now, suppose at some point we want to do an upgrade. How should we go about doing this protocol upgrade? The problem is that we've got many clients and many servers, and we have to find a way where we don't have to change everything in lockstep. One of the things that happened when it came to discussing how we were going to introduce modules was we were going to say, all right, everybody in the world just stop and change everything to modules. And of course, things don't work that way. So there had to be a way in which we could do a reasonable upgrade. And that was an important design consideration. And similarly, when you're designing software, there has to be a process for doing an upgrade that doesn't require somebody flips a switch and everything immediately upgrades, because that's not realistic unless you're a company that has that kind of control over everything, including your clients, which is, again, a rare thing indeed. So we're going to talk more about this later. Now let's take a look at some code. So I do want to mention that I put some code in here because this is real stuff. It's real code. Also, I want to note that in this first book, I deliberately avoided use of modern C++ because it wasn't the point of the architecture volume. It specifically was designed for people who have a lot of experience, but might not be familiar with some of the details of modern C++. So against much advice, I kept the code to be it's a subset of C++20 that is C++03 as well. And where it was appropriate, I noted where you might do something different. Turns out that when you're designing software, very, very, very little matters whether it's C++03, 11, 14, 17, or 20. When you're designing it, when you're implementing that, that's another story. But when you're designing it, not so much really. And so I wanted to make sure that this was accessible information. So with that said, you'll see that I'm using just plain old regular vanilla C++ here. And in this particular function, the function would be, it's taking two lists, and you'll notice that in the interface, and you'll notice that we're taking advantage of iterators. And iterators are an important design technique because by using iterators, we allow ourselves to change the implementation of something without necessarily having to rewrite it or insert a method to do it. So here, for example, I'm writing this free function called my_r_abs equal on two lists. I don't have to go to the lists and do anything with them. I simply use the iterators and write the code thus. So I want to write a print statement. So if I have a fancy print statement, again, all I need to do is take the iterators and I'm good to go. And I don't have to go in and modify the piece that I'm working on. So this is an important principle as well. Whenever you're writing something, you want your library to be stable. You want it to be open to extension and closed to modification, particularly source code modification. And if you are going to modify it, it's going to take time. And however you modify it, you want to make sure that it's substitutable for the old one in every piece of code that's written so far. That is a substitution principle that's really important. Probably closer to Liskov substitution than people would normally think Liskov substitution is, which doesn't have to do with inheritance at all, but that's another story. Okay, so that's the interface, and here are the iterators we're using. Moving forward, imagine we have a system that has an account report writer that depends on a PostScript output device that in turn depends on a physical printer. So this arrow from box to box is called the depends on relation, and the report writer, that unit of software, depends physically on the PostScript output device software, which in turn depends physically on the external printer, if that makes sense. So here we have a system where we have three different report writers, and they all depend on the PostScript output device, and they're all implemented in terms of a collection of library software, and thus they don't have to be as large as they might otherwise have to be if we had just copy-pasted a huge implementation over to the next and then to the next. This is what I would call well-factored software. It's hierarchically reusable. Each piece makes sense in itself. It's unit tested and so on. All right, imagine we have this kind of situation where we have a PostScript output device and we have three different report writers written to it. And now it turns out that we have an ASCII output device and we want to have the same capability. And now suppose we have a Windows output device and we want to have the same capability. What can we do? So there are different ways to approach this problem. This is not one of them. One might consider that we create a general output device manager and have it depend on all three different output devices, and then have the report writers depend on the output device manager. And as you can see, this doesn't have any cycles. It doesn't have any long distance friendship. In theory, it's fine. But in practice, it's not fine at all, because why would you ever need, in an application that's running on a Linux set of processors, why would you ever want to have a Windows printer hooked up to it? So having to link that in via the output device manager is insane. And of course, we're not going to do that. So bad idea. This is an example where good old object-oriented programming is our friend. Could we do it with generic programming? Perhaps, but not reasonably, because of the tight compile time coupling that would be achieved, and for no purpose. Here we have the loosely coupled bits that implement and use the abstract interface. This is, I think at some point in time, we forgot that there was a reason why we have this kind of code. It's not the highest performance code, but it's loosely coupled. And when you're talking about very large systems, the ability to not link in a huge piece of code matters. So again, when it comes to scale, you have to decide at what threshold you no longer want to have the tight compile time coupling, and you'd prefer to have the looser, more flexible link time coupling. So here's our output device. It's an abstract interface. Here are our implementations of the abstract interface. here are our users of the abstract interface, and overall, they all depend on this body of software that's hierarchically reusable. Again, this is well-factored software. So another thing is, any kind of software has that has somebody who's calling the shots, let's say a business unit or whatever, says you have to make this system do this. You can have at most one of them. Otherwise, if you have many of them, you would in fact have none, because what you're doing is you're supplying something that makes sense abstractly and not for any one particular client. Now, if you have multiple masters, then you get something like this flattened green toaster toothbrush with flag, because everybody's asking you to do something different. And as soon as you have something that's in conflict, you have a real problem. So again, this is something that we have to look out for. We can't have 3 different people telling us what to do. We can have one person telling us what to do, and then we have to make changes, or we can decide to do something that people need and leave it alone. Next step, physical design. What does that mean? Well, 20 years ago, people would have maybe had little idea. I first described this in the 1996 book, Large Scale C++ Software Design. And of course, it's reprised in the 2020 book that we're looking at now. Physical design, noun, the arrangement of source code within files and files within libraries, and verb transitive, to partition source code among files and files among libraries. So physical design exists. It might be accidental or it might be deliberate. And the art of physical design, of making something that is easy to understand, test, and maintain, is a critically important aspect of sound, scalable development. So at the heart of this all, the smallest unit of physical design that we address is the component. It has a header file, an implementation file, and a test driver file. And testing is something that's covered in depth in volume 3. It happened to have been the first volume that I wrote a long time ago. And it's got a tremendous amount of information that needs to be let out. I just have to get to it. But it was the first volume. It started with volume 3, then volume 1, then volume 2. And anyway, now we're going to look at some code. And I just want to state that the code is here as a picture, not necessarily to read, but to give you an idea. When we write component files, at the top, the first line of code is the name of the file, so we know what we're talking about when we see it on the printer or whatever. And that's part of the design methodology. So I'll just put it in there. So this thing is called mystack.h, and this is an example of a helper class inside the header file for the mystack component. And here are some free operators for that helper class. And here is the flagship class stack, and it has data members, and it has in its public interface types, creators, which include the constructors and the destructor. It has manipulators, which are the methods, the non-static methods of the class that are not const. And then it has the accessors, which are the non-static members of the class that are const. Note, by the way, that these categories are independent of domain and have been around for 30 years and are very deliberate. We don't do getter and setter pairs for many reasons. One of them is it's a really bad way to teach people how to write object-oriented programs, because it gets them to sort of write them as if they're structs. And that is not the design preference. What we want to do is we want to get people to think about the interface and how to use that, and leave the implementation out of it for now. Who knows how it's going to be implemented? Of course we know, because whenever we're designers, we're designing the interface and the implementation with sort of a gray box knowledge of each other. But the idea is we want to encapsulate and hide implementation details that aren't relevant for our client. Pushing simplicity out is definitely a design goal for writing hierarchically reusable software, pulling complexity in and so forth. So after the member functions, we have the free functions. And it's really a good idea to avoid putting, I think we all probably know this, we don't put operator equals inside the class and make it a member operator equals, because that's just bad. And years ago, people might not have known that, but I think at this point, people all understand that there are certain operators that we must have that are free. And these are the kinds of ones that are that. The assignment like operators or members, but I digress. So this is the end of the thing. This is where we would put all of the implementation that goes in a header file that isn't intended for to be part of the interface for the human client, but is needed for the compiler. So let's take a look at how we would diagram this in less detail. If you look at this thing, we have a stack const iterator, and it is used in the interface by a stack. So stack uses in its interface stack const iterator. What does uses in the interface mean? Okay, so a function uses a type in its interface if it names it in its signature or as part of its return type. And a class uses a type in its interface if any of its member functions in turn use that type in its interface. Now, if something isn't used in the interface but is still used substantively, we say it's used in the implementation. And in this diagram, we're saying operator double equals doesn't use stack const iterator in its interface, but does in fact use it nonetheless. These logical symbols have physical consequences, and they imply physical dependencies. So that's why it's really important, rather than having to look at the code directly, we can abstract the code and look at it in this higher level logical relationship way. Now we can go even higher, and we can say that a stack component has both a physical interface, which is the stack.h, which is the top of the stack.h, and the physical implementation, which is the bottom of the stack.h and the stack.cpp file. So the component has two physical pieces, the .h and the .cpp. And in fact, every component has two physical pieces, the .h and the .cpp. In theory, we could have more than one CPP for a .h. In practice, we don't need to do that. The only time we'd ever need to do that is if we, for whatever reason, we're on some sort of embedded system and wanted to have sub pieces of our object code be smaller. And again, it's beyond the scope of anything that we would be talking about here. So this is the physical interface, physical implementation. And we can look at many different kinds of components. The simplest would be a component like point that has a single class. You can imagine a container type that has maybe a set and a set iterator. We can imagine something that's more complex like a graph that has ways to address it. You can imagine something that's a whole subsystem like a my simulator. Now, if you notice, the simulator is so complex, it's most likely it's not implemented in a single component, but in fact is implemented in terms of other components through delegation. Whereas the point may itself be the entire implementation, or it's possible even that there are piece parts of the point having that might depend on something else. And again, it really depends on what goes below a point. A point is a pretty simple thing. So there's a good chance that it doesn't depend on anything else. And yet there may be traits, there may be other things that are hiding behind the scenes that even that depends on. So nothing is really is what it appears to be. It's typically built out of something that you would never think of. Anyway, we look at a system here. We have a point. I've shown it at the bottom, but again, it might be at the bottom of this library, where this library depends on some other lower level library that's really just bits and pieces that no one except library builders ever look at. Then we might have something like a map and its iterator, and then we might have something like a matching engine. So the point is at the bottom. The map iterator is a little bit up. It's at level 2, depending on other things. And the matching engine is at the top of the system. Now, you could think of the matching engine as being like the president of a company. The president of the company isn't bigger or necessarily that much smarter than the people in the middle of the company. However, the president gets a lot of stuff done because the president delegates to the vice presidents and the department heads and so on, all the way down to the line managers and the individual workers. So again, each of these components is roughly of similar size, but its scope and what it's able to do is, of course, more as you go up in the physical design levels. So I'm going to take a quick pause here and ask if there are any questions. Victoria, are you there?
Yep, nothing at the moment.
Okay, well, I'll wait another second if anybody has anything. All right, well, either people are, I explained it perfectly well, or everybody left, or the system isn't allowing people to ask questions. But I'm going to continue. There'll be another opportunity right after this analogy. So I'm going to go on. So top-down software design. Top-down software design is a recursive partitioning problem. It attempts to optimize a complex cost function. Well, what do I mean by that? All right, well, here's an analogy. Suppose that we want to write a program to format function documentation that avoids leaving lots of space at the end of a line due to a very long word like my very long type. I'm sure people who have written documentation in interfaces would like the interface to look kind of nice. And when we get this very long, clunky word, it causes this huge gap. And what are we going to do? So what are we going to do? Well, we'd like it to look a little bit more streamlined. What would that look like if we could do that? It wouldn't have this gap here. Wouldn't have that gap here. It would look more like this, which has a nice smooth margin at the end. So now I have a real question. How do you write a program that takes the code on the left and makes it look like the code on the right? Does anybody have any ideas? I'm just seeing if there's any possibility that someone would throw something out there.
Machine learning. I'm just kidding.
I didn't hear what you said.
That machine learning, but I'm just kidding.
Oh, machine learning, right. Well, nobody's saying anything. All right.
Yeah, somebody's saying things. So message from Hami in the chat.
Yeah.
It says, work with the average number of characters per line. Or
okay, work with the average number of characters per line. So my input is going to be this sequence of words, right? That's the input to the program. Is that true? Is it a sequence of words? And the output is going to be a sequence of words with new line positions indicated so that we get the optimal form. We don't want to increase the line lengths, right? But what's happened here is the 2 on the left moved down a line, and the next line stayed the same. And then as you go down, you see of on one line, the of moved to spaces at the end of, and it sort of shifted everything over. So it's a global optimization. So global optimizations require looking at the whole problem and applying a cost function to the whole problem, right? So what does the cost function look like? What is it we're trying to minimize? Because whenever we move a word from one line to the next, we make more space on the previous line and less space on the next line. So if I were to say we wanted to minimize the number of lines of blank lines at the end of the text, that wouldn't be true because they have the same number of blanks at the end. They're distributed differently. So that's not a solution. So what is it we're asking? Sometimes formulating the problem is not so easy. Well, it turns out that this problem was actually given to me by Ron Rivest at MIT 40 years ago, literally 40 years ago, like to the day almost. And it's a wonderful problem. And it turned out it changed my life because as a result of solving this problem, I learned about some interesting techniques that led to at least one patent. So it's good stuff. But anyway, what we need to do here is we need to come up with a cost function that makes the overall text on the right better than the text on the left. And the cost function is this. What we're going to do is we're going to take the sum of the cube. It could be the square, it could be the fourth power, but it's got to be a nonlinear function. We're going to take the sum of the cubes of the length of trailing space for each line. So what that means is that if you have a big trailing space, it's much bigger than if you have a small trailing space, rather than it's equally bigger. If you take the two and sum them, the one that has the big one gets cubed, and that's humongous, and the one that has the little one gets cubed, and that's doesn't add much. If you turn them into two medium-sized ones, that's significantly smaller than the one that was cubed. That's the idea. So we need a cost function, and then we're going to look at this and we're going to apply the cost function. And so here on the left, we had the two at the front, we had a length of 1. And then on the one on the right, we had a 5. And so the next one, we had a gap of 9, and then we had a gap of 5. So 1 plus 9 is 10. But 1 cubed plus 9 cubed is a big number. And 5 cubed plus 5 cubed is a smaller number. And so when we look at this, we look at this, we look, see that, and then we see that. So we come down here and we see that number is that number, 1 plus 729, and 125 plus 125. And we get 730 is greater than 250. So with this cost function, this is better. Okay. Now the question is, all right, now we can actually decide which one is better. We know we have an algorithm to count it. So the question is, how do we find the optimal partition? All right, well, let's see how we might do this. So here again, I'm not expecting you to read this, but I'm just going to give you a tour. We're going to start in the middle. We're going to write a library function that does this for us. Now, what's interesting is if you're an application writer, you start at the top. If you're a library writer, you start in the middle. I'm a library writer mostly these days, so I start in the middle. So here's my XYZA format.h. XYZA is my package name. Format util is my component name, and this is a header file. And I'm going to have this namespace, which happens to be a struct because this is a static method of a struct, and that works out for me because I don't want to put my names into ADL because I have no intention of having that clog my compiler. And that wasn't the original reason. The original reason was this is a good way to aggregate things inside a component, and I don't need them to be across components, but turns out there are many reasons, as described in the book. We have this class method called calculate optimal partition. And this method is a static method of a struct, and it has 4 parameters. And the output is the first one, which is the result, and it's a vector of indices where I'm going to add new lines. And notice that I have a vector of word lengths. I don't care what the word is. I just want to know what its length is. I also want to know what the line length is, and I want to know what the cost function is. And if you were at Vittorio's earlier talk, he talked about a higher level functions. And here's a function that takes another function. So it's a higher level function. It's just a callback, but it still does what it needs to do. And so what does this do? It loads into the specified result the sequence of respective word indices for the specified word length and line length at which to insert the breaks before the word in order to minimize the cumulative result of applying the specified cost function to the number of writing spaces at the end of each line except the last one. So this is a contract. This describes what's going to happen. I just told you what's going to happen. It's going to happen only if you satisfy their preconditions, which are the behavior is undefined unless for each value of I, one less than word length, blah, blah, and the cost function is a monotonically, at least linearly increasing non-negative valued function of its argument. Note that this primitive calculation packs words with no intervening spaces, adding 1 to each element of word length as well as to line length achieves the most frequently desired result. So the last thing I described here is, hey, this thing does something that's not quite what you need. It's 80% of what you need, but it's a piece part that you can use to do 100% of what you need with little additional work. This is important. Had we written it the other way, we couldn't undo it, but because we wrote it this way, if the font happened to be proportionally spaced, you could, instead of putting the word length in characters, you could put the word length in points. and then add 1 point worth of space to the end, and you could achieve the same functionality in a proportional space font. This is just an interesting fact of proper decomposition. And this is an example of a thorough contract. And this is how we roll. So, instead of solving 150% of the problem, solve 80% and make sure that 80% gets used everywhere. That's the message of this slide, plus how we write code. So with that said, here's the top level program, my application. And again, I don't expect you to read it, but here's the top of the file. Here is the nonlinear cost function written out. It's very complex. T times T times T. I think you get the idea. It's not a complex thing to do. And then we have load word, which is a helper function that is malleable. It's whatever we're going to do to get the words into the proper form. And then we're going to have the main program, and the main program is going to call the helper function and load it up. And then it's going to call the utility, basically. And this is the really well factored piece that requires lots of thinking. And then we're going to format it, and we're just going to write out the result. So that's really the application. The interesting bit is the library piece, and what's the algorithm for that? Well, what we're going to do is we're going to do the theoretical answer first. We're going to partition the problem every way we can. We're going to look at every word in the entire text, and we're going to divide the problem in half or in 2 pieces, and we're going to solve it recursively. And we're going to get the best partition on the first half and the best partition on the second half or part. And then we're going to evaluate it. We're going to get a cost function value, and then whichever pair sums to a lower number, we're going to keep that one. That's the plan. So it's a recursive decomposition, much like software development. We're going to evaluate. We say, suppose I design it, suppose I factor the top level problem this way. I'm going to use a static analyzer. I'm going to calculate how good the subpieces are. It's again like a chess problem, right? We're going to decide which one gives us the best solution, and that's the decomposition we're going to have. Now, obviously, this is a much more tractable problem than software development design, but it gives you an intuition as to what goes into the thought process. So if it fits, great, we're done. Otherwise, we have to divide the problem and look at each partition. Then we're going to load the result back, and we're done recursively. And then return the combined result. So that's the pseudocode. This is the actual code for the program. I put it here because I didn't want you to think I was kidding. This is the name of the CPP file for the format util. This is the context that we're going to pass around. If anybody's ever written a recursive implementation, it's much better. You could do it globally, but it's not good to do it globally because that's not reentrance in terms of multiple threads. So you want to pass around one pointer in your recursive calls. So we're going to have, this is going to be that recursive, that pointer that's passed down. Anyway, so we're going to write a function that that takes the that is called recursively, because typically when you write a recursive function, you're going to have the initial function that sets it up and then the one that recurses down to the final solution. And this is the recursive function. And then finally, we get to the top level method. And the top level method is really simple, as you would expect. All it does is take the interface that we present to the client, build up the, set up the initial call and call it. So here what we're doing is we're calling the recursive function that takes a subrange, and we're calling it with the endpoints of the range. That's really all there is. Now, again, this is detail. It's not important. It's here for sort of proof that it exists, and it's in the book. So now, if we do this, if we run this program, unfortunately, it's exponential effort, because every time we partition it, every time we go down a level, we have a huge amount more work to do. So that's bad. The good news is that this particular problem, unlike other very hard problems, doesn't have an exponential number of unique problems to solve. And we know this because if you look at how many partitions there are, right? You define a partition as being a subrange over an interval from A to B. If the first if the beginning of the range is I and the end of the range is J, how many possible subranges are there if there are n elements? And the answer is what? It's O of n squared. So we have n squared problems and we're doing an exponential number we're solving an exponential number of problems. Something's amiss. So we can do something better. And what we can do better is check to see if we've already solved the problem. This is called dynamic programming or memoization. We check to see if the problem's already been solved. If it hasn't, we solve it and then we record the answer. What's cool about this is we don't change the original program at all. We simply do what a programmer should do, which is ask the question, has this problem already been solved? If the problem has already been solved, then just use it. If it hasn't been solved, solve it and put it in the library. Make sense? So this is what dynamic programming is. This is what hierarchically reusable software process does. Okay, so what did we do? So I'm showing you the code. We're going to add a solution cache. We're going to add this solution cache to our context. We're going to add some new code at the top to see if it's in the solution cache. And if it's not, we're going to do everything that we did before, no change. And then we're going to save it at the end. And that's it. So once we do that, we do a depth first sort of traversal of our work. And then once we've got some sub-solutions, we don't recalculate them. To give you some intuition, imagine you've gone to a new job. You were at your old job, and your old job was great. You had everything. You knew where it was, but you went to the new job. The new job's great in a different way, but there are a lot of pieces that you were used to using that aren't there anymore. So what do? The first program you write, you've got to go and create those pieces again, and it's very painful. But once you have them, when you go to write the second program, there are fewer pieces missing. And when you write the third program, there are yet fewer pieces missing. And finally, when you get to the fourth, fifth, and sixth program, it feels like your old place because you have all your piece parts already written for you, so you don't have to write them anew each time you write a new program. Well, imagine you were doing that on an enterprise-wide scale. It makes a huge, huge difference. How huge? Well, so if you look at how this particular problem scales, if the problem size is 1, there's no reuse. If the problem size is 5, there's 81.48% reuse. The problem size is 10, there's 99.7206% reuse. You can read the rest. It grows hugely. And so this is a real problem. This program that we wrote doesn't work on any problem of reasonable size. It doesn't scale. So let's look at some optimizations. What can we do? Well, what we did the first time was we did the keeping track of it with the memoization. And what we did was we just kept the entire solution each time. So every time we solved the problem, we would copy the answer to a new place. This is a kind of reuse, but it's copy-paste reuse. And the problem is that it uses an extra order of magnitude of space that we wouldn't want to use, and that has a problem associated with it. What if instead of copy-paste, we designed a way of doing lookups where the piece that we solved referred to the other pieces that we'd already solved in a tree-like way itself? See how this is connected? So the solution that is the entire range from 0 to 999 is implemented in terms of two solutions, 1 to 0 to 145 and 1 to 146 to 999 and so on recursively. What we've done is we've collected the recursive decomposition of the solution, the best solution in the solution cache. And now we don't have to replicate that long array of indices. And in turn, what we have is we have a node which is a fixed size. And the node will turn out to be analogous to a component in software development because all of our components are approximately the same size, give or take. And by same size, same order of magnitude, that which can be tested from a single test driver without having to have multiple test paths. And that's just a soft boundary on how big we want a component to be. So again, we have this solution, and these are done by reference rather than copy paste. Okay, can we do even better? It's a fixed size node. What about this map? Now, a standard ordered map is a balanced tree, and the balanced tree itself is an unwieldy thing, and it does more than we really need. We don't need to have an ordered map. An unordered map would have worked just as well, but it's still kind of bulky. But it turns out that since we know what we're doing, we know that there are only a quadratic number of solutions, that we can implement it in terms of a triangular array, which is the most compact data structure that we could think of without doing some sort of compression. So this packed data structure has no pointers for nodes and is actually wonderfully efficient. And the lookup time, instead of being logarithmic or expected 1, is exactly 1 with a low constant. So this is even better. So if we look at this original problem, which was intractable, the first one, which was copy-paste, original intractable problem, the next one, which was copy-paste using dynamic programming. The third one, which is the by reference, so that we didn't have to do the copy-paste and we could use each solution in place. And the last one being that we, instead of just using a hash function, we actually place the things where we know they need to be so we can find them quickly. It turns out when you run this program, each time you get a much, much better result. So again, why did I write this program? I found the analogy between text partitioning and program partitioning to be striking, because they have the same properties, and yet one of them reduces to mathematical formula, whereas the other one doesn't. So just to go over what I'm talking about, so you have a subjective cost function versus an objective cost function. You have an application program and suites of an application program suite, a suite of programs, and the entire text, which is again just a big problem. And then when you have factor design, that's partitioning, logical content, words. A leaf component, that's the amount of logic that you fit into something where it's no longer decomposable. That would be a line. A component, well, that's a solution. So hierarchy and a solution could be a leaf component or otherwise. Hierarchically reusable library, a solution cache. Enterprise-wide, globally accessible. Source code copy and paste, independent sub-solution copies, meaning you've got to copy the result and have a new vector representing the same sequence of values instead of having it point to something else. Whereas when you have a software packaging strategy, you have a solution cache organization. When you have curated suite of components, you have solution cache organized in an efficient, predictable way. Uniform component size, again, uniform component size. They're real solution node size. We're now dealing with a fixed size thing that refers to other solutions. Both of these things are stable. In other words, once you have reusable software, once you have a solution, it never changes because other things depend on it. Component dependency, reference to sub-solutions, finding relevant components, finding solutions quickly. So if you just think about it, the problem maps nicely onto a very, very difficult problem in software engineering, namely top-down decomposition. And I hope this gives some intuition. That's the end of my analogy, and I can take some questions. Any questions?
I'm monitoring. I have a question. I was wondering, did we actually end up using this? Did you actually end up using this algorithm tool for some real projects?
Do we use the algorithm for real projects? I mean, in other words, you're asking the algorithm for the for the
minimization of the margin thing. Yeah.
Okay. So I think I understand the question. So the answer to the question would be, this algorithm is way more efficient than anything else that we would do, except if we implemented it using dynamic programming in the very, very most efficient way, which isn't as analogous to what we're talking about. But in practice, if we were trying to do that, we would use the most efficient algorithm. This is a very efficient algorithm, obviously, because it gets the point across. Do we do? If the question is, do we have algorithms that adjust text this way? Yes, we do. We don't use this algorithm to do it, though. Does that answer the question?
Yeah, sounds good. I don't see any other questions so far.
Well, hopefully the idea of thinking about this concrete problem and mapping it onto the other, in some way the dual reinforces each other. Because if I tried to tell you about software decomposition without a concrete problem, there'd be no test driver to see if you were catching the idea. So the idea for me as trying to explain what I'm thinking was to present the two together, and hopefully one where one was concrete, you could look for the abstract in the other, and where the intuition existed in the other anyway, you could map it onto the concrete problem. That was the hope. Anyway, it's explained much more thoroughly and carefully in the book. And keep in mind, these pictures were taken photographically, like literally from the book, and put into a presentation. So this is the verbal version of a book chapter that describes all of these ideas with many more examples in much more detail. The idea is this is the talk version of chapter 0, which is the motivation for why we do this stuff. In the final section here, in the final segment, what I'm going to do is say, okay, why did we bother with all of this? Because it provides some real advantages at scale. So that's what I'm going to go to next. Okay, so if you're in the financial industry and you get a new financial product and you want to make money, you want to be the first to do it because everybody else is going to catch up. So as soon as you come up with this idea, whatever it is, you want to get it to market as soon as possible. Let's say that the idea starts at 0 and you get it to market at T1. The next company gets it there at T2. The next company is not making as much money. You're making the money between T1 and T2. That's all your money, so to speak. The more companies that join, and the further you go, it's going to approach a steady state. T2 wouldn't be the second company. T2 would be the fifth company, just to be clear, because the thing is going down as more companies join. But when you get there first, you have the monopoly. So that's the idea. Now, you could always write something quickly and then write it again. They say that there's never enough time to do it right. There's always enough time to do it over. I hate that. There's truth to that. The trick is, if we do write our software properly, we can do it quickly and right the first time. And the little bit that we have to write that isn't already there, we can write that quickly and rewrite that, so we can still do that. But the great bulk of what we had to do is already there, as we'll see. So that's good news. Another approach is we could just put more people on it. I suppose everybody knows that this is a bad idea, right? Because effort doesn't work that way. And I won't belabor the point. The way effort does work, though, is you get a few people working on a project like a book or a program or whatever, and initially there's a ramp-up period, and I'm sure Vittorio will back me up on this, and you get to a point where everybody's working on the project. They know exactly what they need to do. We've established what the parameters are, and we just got to work and work and work, and at some point, we have to ship it because the defect rate has reached a point where it's not disastrous. And that's this sort of power curve. And this has been demonstrated by a work with Barry Beam in the 80s. And it's just a known thing. I mean, if you've ever worked on any kind of project, projects look like this. So what is software capital? Its charter is to reduce time to market for future applications and products. When I first came up with this, literally 25 years ago, the term is actually borrowed from a coworker at Bear Stearns who came up with the term, and is very similar to another term. But its charter is really the point. But when I sort of started telling people, no one would believe me. So it has a secondary purpose, which is to reduce the effort resulting from maintenance, and that is still true. But the real benefit, it's like the primary reason, is to reduce time to market for future products. So we want the code to be easy to understand. We want it to be easy to use. Now, this is kind of motherhood and apple pie, and they're not quite the same thing. Easy to understand means you can get into to using it, like you can understand it. It's not so complex that there's a barrier to entry, which is different from easy to use, because if it's easy to use and it's also easy to misuse, then there's a problem. So you could be easy to understand and also not so easy to use properly. So that's an issue. And here's a great segue to the book that Vittorio and I are writing, which he talked about earlier today, which is you really want to, when you're looking at C++ features, modern C++ features, you want to pick those features that are easy to understand and hard to misuse, and teach those first. Anyway, the next one is, it's very important for the code to be high performing, because if it's not, people will write their own. I have seen it over and over. You write something, if there's one assembly instruction that could possibly be omitted, people go, that's slow, I'll write it myself. So we really try to write our code in a way that you'd have to be out of your mind to try to rewrite it, because it's that efficient. Again, this is necessary for people to willingly reuse your code. Then it has to be portable. If it's not portable and a new platform comes along, you're putting your company at risk. So it really has to stay within the literal definition of the standard, or you have to you take the responsibility on yourself to know that every future platform is going to support this thing in the way you think it is. So you have to keep that in mind. And then finally, it has to be reliable, and no core dumps, no memory leaks, no incorrect result, no bugs, no, we're not kidding. How do you achieve that? Well, the way you achieve that is by decomposing the problem into something so small and independent that it can be tested in isolation. And then you test each higher level piece in terms of those pieces, like Dijkstra said, that have already been tested thoroughly. That is the only way I know how to write software reliably. Every other way is by guess and by gosh. So if it's important to write easy to understand, easy to use, high performing, portable, and reliable software in a way that reduces time to market for future products, this would be the way. Okay, so imagine this, I'll call it like the Home Depot, or I don't know what we would call it in the UK, but there are these home improvement centers, and they're in the US, certainly, I'm sure you have them there. Vast cavernous places where they have all kinds of piece parts, and they're in different rows, and you go in and you just get what you need, whether they're hammers or materials or light fixtures or whatever they are for home improvement. Now, in this particular home improvement store, everything that's in row 1 was made by the same company. It was just made here. And everything in row 2 was made here too, but it's built out of pieces used in row 1. And everything in row 3 is same company, built out of pieces used in rows 1 and 2. But instead of being, standard physical things, It's more theoretical. It's actually that they're built out of those things by reference. And so when we go to this store, this repository of software capital, we decide what we need. And then let's say it's F, and we pull it out, and we get, instead of a by value copy, we get a by reference copy of F that we can then use. And so when we link it into our executable, all those things we didn't need aren't there. And that's a beautiful thing. That makes sense. That's what our linker does for us. Anyway, so here we are. Here is our executable program that does F. And now we can use F. So what did we do? We started off with our original, back in 2020, we started off with our original faster, better, cheaper design space. And we not only moved it out by improving the software capital we had to draw from, but we also moved it in. And what I mean by that is, because we already have prefabricated components, it's got to be cheaper, it's got to be faster, and because of the amount of effort we put into it, it's got to be better than anything you could do otherwise. So by using the software capital, you get faster, better, cheaper all at once. You can't make it so expensive or so poor or so slow, because much of the work's already been done and done well. So over time, if you didn't do this, you might see some slight improvement in productivity due to experience, but eventually it would decay with the cost of ownership. This curve is very forgiving. It doesn't look like this at all. Very early on, we had an experience where we were hiring people just to maintain code without actually adding new features. This was many, almost 20 years ago. And that really resonated with me. And we try very hard now not to let code get to the point where we have people in maintenance mode. If you find yourself maintaining code, then that code is a liability. So as I said, this figure is generous. On the other hand, if you take a small group of people, let's call them M from the original N, and you have them work on software capital, there will come a point where that added contribution takes off. So at T1, the software capital becomes noticeable. At T2, the total productivity, the rate of productivity crosses, and then pretty soon after that, the total productivity, the area under the curve, if you will, becomes much larger. So this is just a schematic to give you an idea. And if you want to ask me, what's the trade-off? It depends on what M is as to what T1 and T2 are. It depends on the organization. It depends on the quality of the people involved. I mean, it does take a certain breed of people to initiate a software capital repository in a company. I mean, they're not your typical folk. They have to understand applications. They have to understand libraries. They have to understand a lot of stuff. But those people are valuable people because they make everybody more productive and the company more money and less in jeopardy in the long term. So that's the critical point, T2. And we never look back. So let's say we take an application. We have an application, and there's no software capital yet. And we come along and we look at it and we go, oh, yeah. Now, the truth is that some software capital, you don't care what the application is. You have to write it before you ever see an application because every application needs it. So let's assume that's already been written. And now we're talking about a slightly higher level library. We look at the application and we say, these pieces would be useful. And so we refit that application in the second version to depend on that. So that application's been refactored and we've started our software capital repository at this level in the enterprise. Another application comes along and it takes advantage of it and we see, there's some more pieces. So we refactor it. Now we have this second version of the application and more software capital. Third application comes along and the process continues. The point being that over time, there's less and less work to do more and more complex applications. So we do see a feedback loop and a definite synergy between the two. And it is a cost-effective way to do business. Now back to that thing we talked about earlier, where we were talking about the proxy. What happens if we want to create a new thing, a new X it requires a change in U? We could copy the entire system over, make the change, and now we'd have two big pieces of code with only slight differences. But we're not going to do that. Instead, we're going to do something like this. I actually drew this picture in ASCII for the book, and they made it look like this, and I liked my ASCII picture. But anyway, as you can see, we have two parallel systems that share much of the common implementation. And this is a super important diagram to understand how we do hierarchically reusable design. This works in every situation except where X is a vocabulary type. In that case, the problem is more extreme. And that requires getting vocabulary interfaces right, vocabulary type interfaces right from the beginning. And this is how we solve our HTTP upgrade, is that we'll have two parallel systems and people will opt in to the change. Anyway, so this is what a large program would look like if we did it right. This is what a large system would look like, and that program is just an embedded application in the system. In an entire enterprise, we would expect to have a pile of low-level reusable components. We would expect to have piles of medium-level middleware hierarchically reusable components, and we'd expect to have a whole bunch of application-level hierarchically reusable components, and then a bunch of applications, something like this. Without that, we get something like this, which ain't at all maintainable, and the applications get bigger and bigger and bigger and consume all available oxygen in the room, and eventually you die. So this is a bad idea. The ultimate goal is to have a small, very expensive collection of highly hierarchically reusable components. Now, I say they're expensive, but they're nowhere near as expensive as having that functionality duplicated across all versions of all applications and having to maintain all of those separately, because the quality of each of those will quickly go to heck, and the cost of maintaining them will kill you. Whereas here, there's nothing to maintain because that software capital is as good as it's going to be. Very, very high performance, easy to understand, easy to use, and so on. Now, when I say there's nothing to maintain, obviously, there is something to maintain because the BD group at Bloomberg maintains such a set of software and enhances it, and is also the group that adds to it, because you don't have application developers writing highly reusable code. They write applications. You need a team of people whose reason for existence, raison d'etre, is to write software capital. You can have people contribute software capital, but it has to be managed appropriately so that it's tightly integrated and highly reusable. Much like standard components are not written ad hoc and submitted to the standard. They're written by they're designed by a team of people who have an understanding of how these things interoperate. So with that, I am done. Thank you. Any questions? And I should note, we are hiring. Any questions?
Yep, some questions. So question from Richard. When starting a project, how do you practically measure software reuse and quantify its benefits? Any real-world figures and examples are appreciated.
Okay, so if I understand the question, when you're starting a project, how do you quantify reuse? This is probably one of the hardest things to do, because to really do those kinds of questions right, you would have a controlled experiment. You would have two companies doing the same thing, one with a group that's doing this and one without. The experiment at Bloomberg was done over 20 years. and we have only the one thing where I was injected in 2001. It's 2021. This book was written. These figures and everything in it was started in 1998, and it took me 20 years to write. And these pictures actually existed 20 years ago, and they haven't changed. The only thing that changed is they came to fruition. So what I can tell you is anecdotal, but it's real. It was predicted, and it came to pass. I don't think Bloomberg would be the same place if it hadn't done this. But I can't give you a numerical, value. We took X people, and the productivity improvement per year was 1.03%. It isn't like that. It's kind of like, had we not done this, we would be in deep doo-doo. That's the technical term.
Cool. Another question from Daniel. How large should a software capital team be, ideally? So the size of the team, what do you think it should be? Okay,
so excellent. Before I started this whole experience, I would have said, if it's 5% of your organization, it's too small. If it's 50%, it's too large. I'll stick to that, but I'll say that it's probably okay for a mature software infrastructure to have a smaller percentage than it is starting up. If I were starting a company, I would put everybody in my company of 5 people working on software infrastructure to begin with, because there's a certain amount of stuff that just has to get done. Then as you grow over time, you'll need to write applications. And I would say that in a semi-mature organization, having one infrastructure engineer for, now again, it's kind of jaded here because there's really truly amazing software capital core stuff like the standard template library, which is just, super uber. Then there's like the low-level core library at a large company like Bloomberg, which is pretty good. And then there's kind of like software infrastructure at a company like Bloomberg, which is good, but it's clearly not at the same level because we go out of business, but it's still the same idea. So it depends on what you're asking. If you're talking about, let's say, software infrastructure to application development at Bloomberg, a rough guess, it's something like, I'm guessing about 20%. Okay, but that's all of software infrastructure. We're talking about like the core. We're talking about it's really small. It's like less than 1%. In other words, you need a team of people. The team of people we have at Bloomberg collectively that does this kind of work is on the order of, well, all in is on the order of 20. If you understand what I'm saying. I mean, at the very lowest level, everybody considered like people who are employees and contingent workers and all the, kind of the support staff, there are about 20 people at the very, very core who do the most detailed work. But I think to answer your question, 5 to 50%, depending to where you are in your development process.
Cool. I don't see any other questions.
Well, all right. In that case, unless somebody has a quick one, I want to thank Vittorio for helping me out here because I've both of us have been burning it at both ends to get this book, Embracing Modern C++ Safely, done. It is the other end of the spectrum from the book that I worked on for 20 years. This book that we've been working on is all about practical use of C++ 11 and 14, and it's really just a complete, companion. It's completely orthogonal to what we've been talking about here, and incredibly useful at any scale. And I've certainly learned a lot working with Vittorio because he's been teaching this stuff for years, and he knows it cold, and he helped me learn it. And hopefully, in that process, if you guys get a chance, you'll see it coming out in Q2. And anything else?
I think that's it. Thank you very much, John, for your kind words. I have to say it's a pleasure to work with you as well. So.
Oh, absolutely. It's been great. I can't wait for it to be done. Any day now. Any day it will be off. All right, then. I guess thank you all for coming. Enjoy the rest of whatever there is. Is there more tomorrow, or is there another day? Or whatever. Enjoy whatever's left. And again, thank you for coming to my talk.